Welcome to the NERACOOS Integrated Nutrient Observatory webinar series. My name is Tom Shaika. I'm with NERACOOS, and I'm going to be providing an introduction to the project and moderating some questions today. So the purpose of this webinar series is to share the results of our Nutrient Observatory project with you. Specifically, we want to show you some of the data from the project, describe the sensors we deployed, present some of the challenges and lessons learned, show you how to access project data, and describe some of our next steps. So first, I'm going to start with a brief overview of NERACOOS, and then a brief overview of the Integrated Nutrient Observatory project. So NERACOOS is part of the U.S. Integrated Ocean Observing System, or the U.S. IOOS, which consists of 11 regional associations which cover the coastal waters of the United States and the Great Lakes. And there's a U.S. IOOS program office that is housed in NOAA. But at the national level, the program consists of a partnership of at least 17 federal agencies, and there are many more partnerships at the regional level. So NERACOOS is the Northeastern Regional Association of Coastal Ocean Observing Systems, and it serves the Northeast region as shown in this map. The NERACOOS mission is to produce, integrate, and communicate high-quality information that helps ensure safety, economic and environmental resilience, and sustainable use of the coastal ocean. NERACOOS is a partnership of many organizations. The image here shows many of the partners who design, develop, maintain, and operate the various elements of the observing system in this region. And this includes a network of oceanographic buoys, coastal radar systems, ocean forecast systems, water level sensors, and a data management system. So now I want to give you a brief introduction into the Integrated Nutrient Observatory project. Our goal was to develop an integrated nutrient observatory within NERACOOS capable of resolving nutrient dynamics at temporal and spatial scales necessary to address critical needs of stakeholders throughout the Northeast region. There had been certainly some successful shorter-term research deployments of automated nutrient sensors in the region, but there was no network of sensors intended to be deployed long-term as part of an operational observing system. And that's what we were trying to achieve with this project. Now, the partners on this project were Seabird Scientific, the University of Rhode Island, University of New Hampshire, University of Connecticut, the University of Maine, the Gulf Maine Research Institute, and NERACOOS. This project was funded by the IOOS Ocean Technology Transition Program. And this program sponsors the transition of emerging marine observing technologies for which there is an existing operational requirement and a demonstrated commitment to integration and use by the ocean observing community to operational mode. Now you can learn more about the OTT program at that link I have there. You can also Google IOOS OTT. You'll get to that same page. You can learn about other OTT projects. And I was told by the IOOS program office that there's likely to be another call for proposals for the OTT program sometime this summer. Typically, OTT projects involve a partnership between a regional association or multiple regional associations, academic institutions, private sector companies, that have developed a sensor technology that's going to be transitioned into operation. So a little bit more about our project. The nutrient sensors selected for this project were the Seabird Suna, a nitrate sensor, and the cyclophosphate sensor. And we did start out with the cycloammonium sensor as part of the project, but Seabird Scientific at a certain point in the project determined they couldn't continue to support that for the project, so the focus is really on the cyclophosphate and the Suna nitrate sensor. Now you're going to learn a lot more about these sensors in our third webinar. So the sensor deployments. This map shows where we propose to deploy the nutrient sensors on existing buoys. You can see that we included various estuarine locations, Long Island Sound, Narragansett Bay, and Great Bay, New Hampshire, as well as the coastal waters of the Gulf of Maine. So this project is really leveraging the existing buoy infrastructure and the expertise at the partner institutions, where there is a tremendous amount of work done to learn how to operate the sensors, integrate the sensors into the existing buoy mooring systems and data systems. Stakeholder engagement was another important component of this project, to make sure stakeholders were aware of the data being collected so we could understand how the data will or may be used, and to help us understand how to display and provide access to the data. So this engagement is ongoing. Some of it's been accomplished through workshops, presentations at various meetings, one-on-one discussions, and this webinar series is part of our engagement activities. The OTT funding for this project, the OTT project is actually officially ending today. However, we are transitioning with support from IUS and support from the EPA. We will be transitioning some of these sensors into operations, and we will continue our engagement activities to make sure that the data can be effectively used. So we have a three-part webinar series scheduled. We decided to present some of the results from the various sensor deployments first. So today you'll be hearing about results from the Gulf of Maine and Long Island Sound. Next week, you'll be hearing about results from Great Bay, New Hampshire, and Narragansett Bay. And then the following Friday, you'll learn more details about the sensors, some of the lessons learned, some of the challenges from operating these sensors, and about data access. Now, if you can't participate in all of these webinars, or if you want to review the webinars, we will be recording them and making them available on our website. We have a lot of participants today, so as you, I think, saw, everybody's going to be on mute, but please feel free to send in questions using the question function on the GoToWebinar control box. We'll try to get through as many questions as we can, but also at the end of the presentation, we'll share contact information for the presenters. So if we don't get to your question, you can follow up with them. So for the first presentation today, I have the pleasure of introducing Dr. David Townsend. He was one of the principal investigators on this project. He's a professor of oceanography at the University of Maine and is the director of the School of Marine Sciences. He's also president of the University of Maine Faculty Senate. Professor Townsend is a Maine native. He received his bachelor's of science degree in zoology at the University of Maine in Orono, a master's of science degree in marine science at Long Island University in New York, and a Ph.D. in oceanography at the University of Maine. After completing this doctorate, he worked 12 years as a research scientist at the Bigelow Laboratory in Boothbay Harbor before joining the faculty at the University of Maine in 1993. His area of research expertise is basic biological oceanography, especially in the Gulf of Maine and Georges Bank regions of the Northwest Atlantic. He has authored or co-authored more than 100 scientific publications covering various aspects of nutrient cycling and plankton dynamics in relation to physical oceanographic processes. His most recent focus has been on understanding the causes of red tides and climate change-induced alterations to the ecology and oceanography of the Gulf of Maine. Throughout his career, he has received more than 50 federal research grants and contracts. In addition to research, he teaches both graduate and undergraduate classes at the University of Maine. And in 2012, he published his textbook, Oceanography and Marine Biology, An Introduction to Ocean Science. He has served on numerous national committees and panels. He has won the Outstanding Teacher Award for the College of NSFA in 2001 and the University of Maine's Distinguished Professor Award in 2006. Okay, let's send it over to Dave.
Okay, let's see. Can everybody see my screen? I guess not. Tom, can you see this?
I can't see your screen yet.
I can see it, Tom and Dave.
Okay. Okay, let's see. Go back here. I need to get rid of this menu on the side here because I can't see my own slides. How do I do that? Oh, hide control panel. Now I can't see my screen. All right, I've screwed up now. Can you guys still see my presentation?
Yep.
How come I can't? Oh. Well, we start this over. I can't. All I see is me. And nobody can hear me, right?
I can hear you, Dave, and I can see your presentation now, but you cannot see your slides.
I cannot see my own slide. Okay, I just had to hide my own camera, I guess. Okay, how's that? Better? You guys can see it, right?
Yes, we can see it.
Okay. Well, since I'm already out of time, we'll rush right through this. First of all, I forgot what the title is that I gave you guys, so it's a little different. I'm going to talk about nutrients and water mass dynamics in the Gulf of Maine. And we'll start out with, assuming everybody knows where the Gulf of Maine is, it's inside this red box here on the left. And this is what it looks like when you remove all the water. And I'm sitting up here right now in Orono. So, of course, the Gulf of Maine is filled with water, but it gets its water from several different sources that flow through the Gulf and out again. It gets relatively fresh and cold Scotian shelf water at shallower depths coming around Nova Scotia, but it also receives warm and salty slope waters at deeper depths and along the bottoms. And it's that slope water that's the source of salt to the Gulf and also the source of nutrients. Of course, it gets some fresh water also from rivers and a small fraction of its nutrient load, but relatively insignificant compared to the deep slope water source of nutrients into the Gulf. To look at the Scotian shelf water, this is very easily visible in satellite images of sea surface temperature. It comes around as a very cold water mass that's clearly visible, as seen in this satellite picture. Slope water, on the other hand, you can't see from the surface because it comes in along the bottom, but Henry Bigelow first described it based on the depth to which the 34 part per thousand isohaline penetrates upward toward the surface, and you can see it coming in through the Northeast Channel between Georges and Browns Bank, hugging to the right because of the Earth's rotation, spilling into Jordan Basin, and eventually spilling throughout the remainder of the Gulf of Maine. Well, as for the slope water sources, there are actually two different types of slope water masses that come into the Gulf of Maine, one from the north, one from the south, and they meet and mix in this area known as the Slope Sea. From the north, we get this relatively cold and fresh, but denser Labrador slope water and shelf water coming from the north. And then from the south, we get our warm slope water, which sort of peels off from beneath and off the side of the Gulf Stream. And that's the warm and salty water that comes in. Now, these two slope waters have quite different nutrient loads, so it's important to know which one is penetrating the Gulf if we're going to put together any kind of a nutrient budget. If we look at the Labrador slope water, shown by a couple of transects here off of Labrador out into the Labrador Sea, down to 1,000 meters and out 400 kilometers, the highest concentration of nitrate is only around 17 micromole. Silicate is sitting here at around 10. But if you look down at the warm slope water mass, highest nitrate is 24 micromoles. Notice it's sitting on top of slightly lower nutrient Labrador seawater here as it's adjacent to the shelf. And silicate's a little bit higher, but not by much. It's only about 14. The main point here is warm slope water has about 7 micromoles more nitrogen than Labrador slope water, but that both of them, both warm slope water and Labrador slope water, have more nitrogen, significantly more nitrogen than silicate. Okay, once that water comes into the Gulf of Maine, along the bottom and at depth, it's mixed upward by winter convective mixing in the wintertime and by tidal mixing throughout the year. A lot of it tends to come up in the northeastern Gulf of Maine through tidal pumping that feeds the eastern Maine coastal current, where it spreads down and across the Gulf. It's also, the Gulf of Maine is the source of nutrients to Georges Bank, but that's not where we're going today. Evidence of this bringing up of nutrients into this Eastern Maine coastal current is shown here in a number of cruises where this is just a slice of nitrate at 10 meters depth. You can see that the only place here in this survey domain that the nutrients are measurable really are there in the Eastern Maine coastal current. Okay, this is how I used to think the Gulf of Maine system worked before about 2007. And then at about that time, we started to see some curious observations. First of all, this is a result of a survey we did in the summer of 2006. We were actually looking for, well, it doesn't matter what we were looking for, we didn't find it. But the point is we were measuring nutrients at the same time. And here's a plot of surface nitrate and surface silicate. And what's odd is that in the Eastern Maine coastal current, which should be getting its water from slope water coming in and being mixed upward into the surface, we have silicate concentrations that are higher than nitrate. So that was a surprise. And it leads to the question, you know, what's going on? So if deep source waters, both warm and slope water and Labrador slope water, both have much higher nitrate than silicate, and if that's the case, but that's not the case in 2006, so we started looking back at some of the historical data to get a handle on what may be going on. And these are just sets of 3 stations, nutrient profiles done in Jordan Basin. 3 stations in 1976, again in 85, and again the ones I just showed you in 2006. Notice that the nitrate, which is the open circles, in 1976 at all of these stations near the bottom. Now, just in the deep water is what I want to focus on. Significantly higher nitrate than silicate, which is in keeping with what we just argued based on slope water source of those nutrients. A little while later in 85, notice these lines are coming closer together in the deep water. And then by 2006, all the way down to 230 or so meters, they're the same. Now, if there's no difference between nitrate and silicate by 2006, that's something's going on, because that's impossible if the source of the waters up here in Jordan Basin came through the Northeast Channel as slope water. So this can only be explained by an increased flux of shelf water that is mixing all the way down to the bottom in the interior Gulf of Maine. So we took another look at it based on historical analyses of what data we could find for temperature, salinity, and the nutrients nitrate and silicate back to the 1960s, and they're plotted here. The stations we picked were as close as we could get to the point of entry into the Gulf, and they were all below 100 meters, so we didn't have biology mucking things up. So this should be an indicator of what has come into the Gulf. And so the temperature showed the well-established trend of in the 1960s being cold, the 70s warm, and then it got cooler. The salinity followed that pattern, where it was fresher, then it got saltier, then it got fresher again over time. So these drops are curious, from the warm 70s to today, and the relatively salty 70s to today. And then if we look at the nutrients, we start out, the cold 60s have low nitrate, and then the warm 70s with lots of slope water, very high nitrate, and then it dropped down slightly. Silicate started low, and it went up, and it stayed up through the early 2000s. Now, these data are only for, I think, through 2004, when this is the latest data we have. So this one bar here in 2000 really is not very representative. So the question is, you know, what's going on after the 2000s? And so one of the ways to address this is to take a closer look at some of the data being collected by the NERACOOS buoys. And in particular, I'm going to be showing you some results from the Jordan Basin buoy out here, maintained by Neil Pettigrew here at the University of Maine. So if we look at the complete record, plotted here on the left as temperature on the top and salinity on the bottom, and these are at depths of 200 and 250 meters, in order to get a handle on what's coming into the Gulf of Maine. This sort of violates one of the conceptions that we were brought up to believe, so to speak, and that is bottom waters are constant. They shouldn't be changing. But notice the flip-flop here. We go through warm and cold, and notice that the salinity is coherent with those patterns. You have both warm and salty, cold and fresh, warm and salty, cold and fresh. And then we hit this period in about 2011 where the waters are warm and salty, followed by perhaps some cooling off and freshening of those waters after 2011. So we have these alternating periods of one water mass dominating over another, and then flipping back and forth rather abruptly and not so clear in the last 5 or 8 years. So looking at what those different water masses might be, what the red, the warm and salty, and the cold and fresh might be. We've done a TS analysis without going into the details. What we determined by plotting these in TS space and using a 3-point mixing triangle, that these alternations are mostly due to warm slope water that's alternating with periods of domination by shelf waters. Labrador slope water, which used to be a part of this thinking, and is shown here down in this TS diagram, has only a minor influence now in the Gulf of Maine, and after the 90s and 2000s, it seems to be low, variable, and not correlated with anything we can find. Certainly not the North Atlantic Oscillation, which was heretofore thought to be the case. Okay, so what about nutrients? Well, the first experiment we ran was with an ISIS nitrate sensor, not a SUNA. It's over here. This actually belongs to Jim O'Donnell at the University of Connecticut. He lent it to us. We never gave it back. It's out there in the Gulf of Maine now. It's back. This thing is a tank. It really works great. We had to build a battery case out of a pressure housing that was kicking around. And this is all done by Neil Pettigrews engineers. And anyway, we had to pick a depth and where to put it. So we put it out in Jordan Basin at 100 meters, and just to see what we would find. And what we found was this. This is a record of the temperature and salinity out there at 100 meters from June of 2013 to March of 2014 at 100 meters. And the ISIS data are shown below, but it failed in December that year, so that's where the data end. The circles here are calibration water samples taken at sea at the depth of this sensor. So the thing to notice is we see this general trend that Bigelow described earlier, where warm slope water tends to come into the Gulf of Maine in the fall. But notably here, we see this very sharp increase in salinity, sharp increase in temperature, which we would think is, there's our warm slope water coming in, but instead of nitrate going up, it went down. And so from that, we speculated that this is Gulf Stream water, but based on very little evidence other than a lot of arm waving. So that was our first experiment. Then we bought some SUNAs with this new project and instrumented Jordan Basin mooring more fully. And so those are the results I'm going to show you now. First of all, let's just look at the temperature and salinity record for the period 2003 to just a few weeks ago that Maura Thomas plotted up for me. And here is repeated what I already showed you. It's this oscillation or this alternation of water masses. And but what I didn't show you, because we hadn't collected those data for the earlier analysis, is the last 3 winters, summer-fall periods, we see some of the warmest and saltiest waters in the Gulf of Maine throughout the record. Interestingly, too, before that, we see some of the coldest and freshest waters. So this is a fascinating phenomenon, and I'll speculate more on what that is here, or will I? Yes, I will, shortly. So looking at the data presented here as a cross-section with time through the 1 year here through the fall to winter period of 2017, from October to late winter, showing a section here of temperature, salinity, density anomaly, and nitrate. We see a couple of things. First of all, we see evidence of Scotian shelf water coming in at the surface here in late fall, perhaps, where the waters are a little colder, sitting on top of warmer waters. It's not quite so visible here in the salinity because the sensors really don't have that level of resolution. They're at surface 50 and 100 meters, so it's sort of a guessing job here. But looking at the nitrate data, we see this interesting. Well, first of all, salinity data, we did see some very high salinity water coming in here at the bottom, which we speculated might be Gulf Stream ring water or Gulf Stream water of some kind. Nitrate was fascinating because we saw apparently coming in with Scotian shelf water, not necessarily low nitrate water, but high nitrate water sitting on top of low nitrate water and then increasing with depth again. That was a very curious phenomenon. This is a close-up showing how it seems to sandwich a layer beneath it at 50 meters, which is lower in nitrate. Anyway, had never seen anything like this before. We did not have a ship out there to take a water sample to confirm that nitrate was in fact higher at the surface than just beneath it. But you know, those are the data we did get. So looking at more closely at these data and looking at the daily means here of temperature, salinity, well, I've hidden the temperature, sorry, you can't see that, but salinity, sigma T, and nitrate. We noticed that in that fall period, we see the surface density, and this is the axes here are reversed so that everything sort of follows the trend we see with your eye, where something goes down, it's getting colder, and so anyway, and saltier. Anyway, so this is the we see the sharp increase in density here in October, November. At the same time, we also see a sharp increase in salinity, and these are at the surface now. And so at the same time, here are the nitrate values. This brownish color here is the surface nitrate, and it is showing, again, the nitrate concentrations here on the axis are reversed. The highest are downward, so we see this higher nitrate at the surface than we do at 20 and 50 meters. So this dense and salty high nitrate surface water, it would seem, based on the density and salinities, could not possibly be Scotian shelf water. So it leaves open, what the hell is it? So now we look at the bottom water for that same overwintering period, 2016, 2017, and I've put here in a green square this phenomenon where we see this abrupt increase in bottom water salinity and temperature in July that year. And again, plotting the data as just shown you earlier for the previous year with these cross sections. First of all, again, we see high salinity water coming in at the bottom in the fall, and very high, 34.8. Had never seen salinities this high, by the way, in the interior Gulf of Maine. Northeast Channel, yes, but never inside in Jordan Basin here. And we see the same phenomenon of a high nitrate layer overriding the 50. Now, this is not due to instrument error, or if it is, it's a hell of a coincidence because we had to swap instruments around when the mooring was turned around. So the instrument that recorded, this is a different instrument at the surface than the one that recorded it the previous year. Okay, now, taking a look at the deep and bottom waters in 2017, I want to call your attention to this phenomenon where we see first occurring at 250 meters, then at 200 meters, then at 150 meters, we see this what appears to be an abrupt arrival, if you will, of waters coming in to Jordan Basin. It's shown in the temperature, but we lost the salinity sensor here at 250 meters, so I can only show you 200 and 150. So the temperatures went up and the salinities went down, but they arrived first at the bottom, then the next level up, then the next level up, etc. So we're going to look more closely here at that phenomenon and line it up with the nitrate sensor and see if we can make some sense of it. So here's the phenomenon I just told you about. There seems to be a wedge-like of water that comes in, appearing first at 250 meters, second at 200 meters, and third at 150 meters. Shown most clear with temperature. Again, we don't have the 250 meter salinity, but the same phenomenon of increasing salinity as that appears. And then looking at how that corresponds with nitrate, this is when it got really fascinating, and that is that normally if this were slope water coming in, warm slope water, we would expect the nitrate to rise. And don't be misled here. This is going in the wrong direction because the axis is reversed. So the nitrate, while this water was coming in, this high salinity warm water, the nitrate actually decreases. It started out at about 20 micromoles in July, and it decreased to about 17.5 in September as both temperature and salinity abruptly rose. Nitrate then, after this event, about this period forward, where it's more constant, either through simple diffusion, but it seemed to adjust back to a level of about 19.6 by mid-November. So, what is that water? Well, if it were warm slope water, it would have temperature and salinity characteristics that would reflect the origin of those waters, but most significantly, it would be not just warm and salty, but it would have 22 to 24 micromole, and of course, there would be a modification of that water mass as it comes into the Gulf of Maine and Jordan Basin, and so all of these would be modified somewhat. If it's Gulf Stream water, it would have much warmer, much more saline, but lower nitrate. Now, here's a cross-section that I showed you earlier out across the Gulf Stream, where we've got nitrate at 24 micromoles on one side of the Gulf Stream front and between 1 and 3 on the other. The temperature is much warmer on the other side here, and of course the salinity is much higher as well. So it's beginning to look like this is Gulf Stream water that came into the Gulf of Maine, but it only can be verified. Well, it's not really verified, but if we put those samples here in this TS diagram that we used earlier to identify warm slope water versus shelf water and extend the axes to account for Gulf Stream water up here and extend our 3-point mixing diagram to include Gulf Stream water, we see that we get a nice line between what we know as deep Gulf of Maine water beforehand on a straight line up to the source waters of Gulf Stream water. So it certainly has been very much modified by becoming colder and fresher, but it is still, nonetheless, some of the warmest and saltiest waters that we've seen in the interior Gulf of Maine before. And that's it. So I did finish in just over 20 minutes, Tom. That's my last slide.
Thanks, Dave. So we do have time to take a few questions for our next presentation. So if you want to type those in, I'll take a few questions, and then if we don't get to them all, maybe we can do some at the end, or you can contact Dave. So here's a question, Dave. What role, if any, do you think biological mediation might be having on your observations? For example, higher temperature often results in nitrogen movement into biomass and switches between nitrate and silicate limitation can send different concentration signals.
The biology is important down deep. These are deep water masses we're talking about, 200 and 250 meters. So photosynthesis, phytoplankton production is going to have very little influence. But sediment denitrification is influential. And that was, sediment denitrification is one of the arguments we made in 2010 to explain these declining nitrate but increasing silicate levels that we saw in our decadal historical analysis, that as the Gulf of Maine became more dominated by shelf water, we were getting waters that were traversing from the Grand Banks of Newfoundland, the Scotian Shelf, and into the Gulf of Maine that had plenty of opportunity to denitrify, which to experience sediment denitrification of the deep waters. That would reduce the nitrate. The silicate gets another kick from waters coming out of the Gulf of St. Lawrence, but because it is a coastal flow, a coastally trapped baroclinic flow coming down from the Labrador Sea, any silicate that is taken up by diatom blooms that fall out, they will be falling out onto the shelf where they're readily available for regeneration. So with distance downstream, one would expect silicate to become enriched by the time it gets to the Gulf of Maine. So that was our explanation for how that changed decadally from the 70s to the 2000s. But most recently, I'm not sure what's going on. Other than, I realize now I didn't actually repeat what I should have via the last sentence of the slide here, and that is that we would not have been able to state with any assurance that these warm and salty waters that we're seeing most recently are from the Gulf Stream without the nitrate data. It's because the nitrate decreased rather than increased. It was going in the wrong direction with the rise in temperature and salinity. That was the hint, the strong hint, or the proof, if you will, that it's Gulf Stream water, which is very, very low in nitrate. Biologically, though, I will throw out that it may not be just coincidental that these two events that I've got circled here in this last slide, there is a third event that's not on this slide, but it's on the earlier one, that happened again this past year. But those 2 years I'm showing there in the circles were the same years that, for the first time ever, Pseudonychia australis, the pennate diatom that is responsible for amnesic shellfish poisoning, was recorded in the eastern coastal Gulf of Maine, near the point where we'd expect uplying waters to occur near in eastern Maine or the eastern Maine coastal current. So one has to wonder, did the Gulf Stream waters that we see penetrating the interior of the Gulf bring in this species that had never been recorded in the Gulf of Maine before? And so, whereas we have seen these alternations of temperature and salinity over time until the last 2 or 3 years, they seem to be holding in a warm phase with some hints of wanting to cool off and freshen, but then they would spring back. And now they've sprung to another state where there seems to be a lot saltier and warmer water coming into the Gulf of Maine. How that's going to influence the biology in the Gulf, whether it is significantly lowering the nitrate load that's coming in by displacing warm slope water, With only one mooring, one point in space, it's kind of hard to say. The temporal resolution is good, but we have no idea what these volumes of fluxes are. I don't think I answered the question, but.
Thanks, Dave. There are several other questions, but I do want to get to Kay's presentation so we have time to hear her presentation. And then we can take more questions at the end. And if people want to, we could even stay a little longer after 2 o'clock to do a few more questions. But I do want to switch over to Kay's presentation at this point. So the next presentation is going to be from Kay Howard Strobel from the University of Connecticut. She's a graduate of the Virginia Institute of Marine Science, the School of Marine Sciences of the College of William and Mary, and has been working at the University of Connecticut in marine sciences for nearly 30 years. Her early work was with Frank Boland, looking at sediment transport, circulation, and water quality issues in Long Island Sound. She worked with Frank establishing the first observation buoys transmitting data back in real time. For the past 10 years, Kay has been working with Jim O'Donnell, expanding and developing the capability and products of the buoys that provide for a vast group of users, as well as other projects with Jim looking at sea level rise and coastal resiliency in Long Island Sound. So I think Kay is up and ready to go.
Can you hear me okay?
It sounds good, Kay.
Okay, just checking. Okay, I'll be talking about initial observations of nitrate and phosphate from western Long Island Sound. This is a map of the current status of our buoys that are in Long Island Sound. We've had these out for the past 15 years. Our focus will be here on western Long Island Sound. RG is a seasonal buoy. All these buoys were initially put out to look at the dissolved oxygen concentration at the bottom and the issue of hypoxia in western Sound. As we know, the western end is populated by millions of people and supports a $1 billion recreational and commercial fishing industry. And figuring out hypoxia was an important problem to solve. So I'm going to focus on western. Right now, these buoys are being serviced and will be turned around and put out early spring. This is zooming in on our buoy of focus, how close it is to Execution Rocks, where it sits with relation to New York City. We have two nutrient sensors on the western Long Island Sound buoy at the surface. This box here showing us where I'm going to be focusing our talk on today. We do have at the bottom of western 2 other sensors that EPA has funded us for, looking at ocean acidification, but that'll be a topic of another talk. And why are we worried about nutrients in Long Island Sound? Here's a simple, well, not simple, a schematic of the nitrogen cycle in Long Island Sound. The biggest issue being that we have anthropogenic eutrophication or enhancement of nitrogen, which ultimately affects the duration, magnitude, and onset of hypoxia. So we've been funded to put our buoys out, initially to look at hypoxia, but now to start looking at how high-frequency nutrient data can further elucidate what we know about the hypoxic cycle. Which we already do pretty well with hypoxia, because over the past 15, 20 years, we've been sampling dissolved oxygen in Long Island Sound at a high frequency. We're able to come up with these products that can be used by managers. We can forecast hypoxic concentration real time, and we can plot the data in real time and see how a particular year is doing relative to other years. This is our Western Long Island Sound buoy. Here is our surface DO sensor, salinity, and temperature. Seabird's Microcat Model 37. We also have on this buoy, looking down, an RDI ADCP to look at currents. This is the Seabird Suna nitrate sensor. It's got a brush that sweeps through the optical pathway, keep it clear. But as you'll see, this doesn't always work. And this is the Seabird hydrocycle phosphate sensor. All at the surface, about a meter below the surface water elevation. This is just a picture before deployment. Not only do we have those surface sensors, this is the wire going down. This is our middle package, which is only right now a CTD conductivity temperature depth sensor. And then down at the very bottom, we have the ocean acidification sensors, PCO2, pH, and then right under here are the bottom DO sensors. And this is just a close-up of our bottom DO sensors. All strung out off the stern of the deck with a 3,000-pound anchor to hold it all in place. This is a shameless plug for those of you who live in Long Island Sound and know people who go fishing. To keep clear, do not anchor. We find routinely these large lures wrapped around the bottom. This particular one up top had steel wire that had wrapped around the PCO2 sensor. So if you have friends that fish, tell them to please stay away from the buoys. This is just a close-up. We are high-frequency sampling. I'm talking every 15 minutes. It's transmitted in real time via cell modem. We have a lot of power out there to help. The nitrate sensor has a lamp that comes on and warms up. Phosphate sensor samples for up to 10, 15 minutes at a time. It takes a lot to run these things. And this is up close of the data coming into our data loggers, and here is our wireless modem that transmits it back to the lab in real time. I consider Western and Long Island Sound pretty much a very extreme environment. This is on recovery. These sensors come back, hydroids, propellids, mussels. I will say this is the copper guard that we have on the Seabird CTD. It does a pretty good job. That's about the only thing you can tell in that massive instrument there. This is our phosphate sensor. This is where water is taken in to the phosphate sensor, as you can see. When you're near surface in a sunny, warm environment, it gets fouled pretty quickly. This is our Suna. That's an oyster shell here. Despite the wiper, you can see barnacles are growing in there. We have corrosion on the sensor. As we learn to use these instruments and how to better maintain and faster swap out.
That's what it looks like in Long Island Sound.
Better results. Here is our first season with the nitrate sensor. These are validation points. We took discrete water samples. The time series is beautiful. It's offset a little. We're still trying to reconcile the differences here, but it's a really nice time series. Down at this end, it gets noisy, and we thought maybe this is fouling. Wasn't clear what we were seeing yet. You blow it up, we have these nice dial signals, which we need to investigate further. Big pulses of data from our first season. We're still looking at this, and then we get our second season of data. The same thing. We're doing a little better. Our verification samples are a little closer. These straight lines are just data gaps in the transmission back to the lab. They have to be backfilled, and just hasn't been done yet. Our verification samples, getting a little better, working on this. This a little noisy. At first, it's like, is this fouling? But then you blow up that noisy, and again, you get this really nice dial signal on top of some pulses. I have overlain on this for the moment salinity. One of the questions is, why is it so noisy? What is the variability in? Is this salinity being a proxy for fresh water? Could this be deposition from rain, local, immediate in the vicinity? Is this runoff with somewhat of a lag? These are things we're starting to investigate as this data comes back. The nutrient dynamics in Long Island Sound are still not fully understood, or not well understood at all. Bottom, we don't even have a sensor down at bottom, but the bottom dynamics could be contributing to what we see here. We don't know yet. In terms of these sensors providing more questions, they did a really good job. Here is where I'm just trying to show that we have the nitrogen coming in from precipitation, runoff leading to the eutrophication, and how this could be affecting our magnitude and duration evolution of hypoxia. We also looked at, or I started to look at, maybe this noise could be bubble-induced wind. This is wave data from that same period. We do get this year, starting in September, it got very wavy. There's a lot of wave energy here. We need to filter this data and start doing some correlations and covariance to see what's going on. This is looking at the runoff. Again, this not as good as precipitation. I need to look at the precipitation data because there's going to be a lag here. But runoff starts to pick up. Here at the end, we have these very high values in the late fall, micromolars of nitrates. Our phosphate sensor, in that previous picture, we had seen that the filter clogs up pretty quickly. When we first put out phosphate, they had a different filter setup. They were smaller, and it did not last very long before bubbles and fouling clogged it. Since then, they have put in a larger filter with a copper screen, and we decreased our sampling time. Still relatively high frequency. Connecticut Deep goes out there every 2 weeks in the summer. We are collecting data real time every 3 hours, phosphate. Much better, much longer record, still relatively low concentration. The Seabird cyclophosphates were very cleverly designed by Seabird in that you get quality flags as things go wrong. And as the filters started to clog, the data gets flagged immediately as suspect. This is this season's phosphate data. We see a little more variability. Lasted about a month or so, but we had a very warm, we had problems with that sensor. And again, the filter starts to clog. As we get better with the sensor, I think the bottom line is just 100% swap in and swap out. We need to have 2 of everything to keep things fresh and going for extended periods of time. One of the things we're going to be doing is, with that data that we've collected from Western Sound and all the questions it's raised, is EPA has funded us for putting sensors at the surface on Execution and Archie and Central Long Island Sound, and we'll be able to develop a gradient, a surface gradient of nitrate and just nitrate concentrations. And to answer some of those questions, we've also been funded to put out, this is a Seabird Fluorometer turbidity meter. We'll be able to get fluorescence and NTU concentrations to augment that variability that we see in the record. And then these are, we'll have 3 more nitrate sensors to put out with these at the surface along the sound. And then this is just a, this season coming up, our status will be those 4 buoys going down the axis of the sound, our usual, all our usual sensors, primarily looking at dissolved oxygen. We'll have a nitrate sensor on each buoy at the surface, and we'll have fluorescence collecting data at the surface on each buoy. We will still only have phosphate on Western Long Island Sound. And that's the end of my talk. It's just a preliminary presentation of what we see in the questions raised with our data. We've only been at it for 2 seasons, and I think it's raised many interesting issues. Ultimately, being able to put into a similar model like hypoxic to be able to predict and forecast nutrient input. And that's what I have to say, Tom.
All right, thank you very much, Kay. So what I'll do now, we have 5 minutes before we're officially supposed to end. So I'll see if there's a few questions for you, Kay, and I know there's questions for Dave that we could go back to as well. So Kay, let's see, there's a question or suggestion that it might be interesting to look at PAR or fluorometry along with the nitrate data to see if biological uptake might explain some of the variation. A diel signal suggests, go ahead.
No, go ahead, keep going.
Okay, the diel signal suggests a biological activity. Also, the pool of water sloshing back and forth with the tide may have an impact, especially with a rich source of nitrate from New York City.
Correct, exactly, yes. And we do have PAR data, and all this needs to, we're getting into that. Yes, it's a very good point. Yes, in the different communities, actually another thing we can do with that is look at our nitrogen phosphorus ratio and look at what kind of communities, phytoplankton, bacterial communities are operating and also affecting that variability. But yes, thanks. There's a lot to be done with that data.
All right, thanks, Kay. At this point, I think I'm going to go back to questions for Dave. Dave, there was a question about, do you have any idea, I think, why there is a seasonal cycle in the Gulf Stream intrusions?
Yeah, I was only because I teach. I happen to be teaching a class that touched upon the position of the shelf breakfront off of the Northeast here. And I can't remember the authors of the paper, but it's a 10, 20-year-old paper that showed that there is a seasonal cycle in the position of the shelf breakfront. It tends to migrate shoreward and seaward, and it comes closest to the continent in the fall. It tends to work its way up in the fall. So, you know, right behind that, of course, is where the Gulf Stream slope water resides, and so it may have something to do with that. I have no idea why that migration occurs seasonally, though.
Thanks, Dave. Okay, another question, I think it was for you, Dave, is how certain are you that the dip in nitrate concentration was not due to horizontal advection of a lateral spatial gradient?
I'm sure it was due to a horizontal advection of waters that were coming in, but we've seen no evidence from all the work we've done in deep basins in the Gulf of Maine, measuring nutrients the past 20 years or so. Once you get down there to 200 250 meters, there's no variability horizontally in the nutrient concentration. So it doesn't seem to be any mechanism that could explain that, where we would see such a reduction in nitrate that would that we saw in these data. I could be wrong, but I just haven't seen any evidence of it.
Another question, I believe, was for Dave. Do you think that Quebec mega dams are causing an impact on the Gulf of Maine?
No.
Okay.
I can elaborate if you want. And the reason is, yeah, I've been getting phone calls from reporters and local politicians, hoping that I would say that, yeah, we got to go to Canada and break all those dams because they're killing the diatoms by locking up all the silicate and particles settling out behind the dams. Because that's a well-known problem in U.S. rivers, where dam construction does result in that. But these dams we're talking about have been up there for a long time, on the order of 100 years. And we know that the slope water silicate concentrations that is naturally coming in with deep water into the Gulf are anywhere from 12 to 14 micromole. And when you consider the volume of water that comes in other words, the bulk tonnage of silicic acid coming into the Gulf of Maine just through slope water influxes far and away dwarfs any signal that we can detect as coming out of the Gulf of St. Lawrence in that surface layer once we place it on a property plot of salinity and silicate, meaning that the zero salinity has the highest silicate concentrations and full seawater salinity would have the lowest. It just doesn't hold up. It certainly is well below 1% of the total silicate flux. The Maine rivers, on the other hand, surveys that we have done in the Gulf of Maine where we go run transects inshore, offshore, Maine rivers do have a significant impact on the silicate concentrations. And we often see higher silicate concentrations near shore, inshore of the Eastern Maine coastal current, that are related to low salinity waters. And in which case the silicate there is higher than the nitrate. But once you go farther offshore, they flip-flop. Nitrate then becomes higher than silicate.
Thanks, Dave. And one other question, I think, just somebody asking if you could repeat your main conclusions, Dave, from your presentation.
Yeah, the main conclusion is the Gulf of Maine is experiencing alternating phases of warm and salty versus cold and fresh waters. So they have been throughout the duration that we've had this Jordan Basin buoy out there, anywhere from 2003 until today. But the last 3 summer-fall periods, we're seeing not just warm, salty water come in, but very warm and very salty water come in that, again, we've concluded ultimately comes from the Gulf Stream. Now, if that's true, if it is Gulf Stream water, then that's never been recorded. Henry Bigelow never mentions it in the interior Gulf of Maine from 100 years ago. He does mention it in the mouth of the Northeast Channel. David Brooks, a number of physical oceanographers that have done surveys, and the NOAA surveys that have been out in the Northeast Channel. Certainly we see Gulf Stream water penetrating the Northeast Channel, but it often goes right back out again, and it never penetrates through the channel into Georges Basin, then across the swell and into Jordan Basin. So by the time we measure it in Jordan Basin, it's in the Gulf of Maine. It's not going back out for another year. That's my conclusion, that we're seeing these alternations. And because of these alternations, back when they were just shelf water versus warm slope water, it was apparently important enough that it could be argued, or I have argued, that it's important to such things as dinoflagellate blooms based on the difference between nitrate and silicate left over after a diatom bloom, whether there would be sufficient nitrate left over to support species succession to dinoflagellates on the one hand. On the other hand, this water also, this warm water that comes in at the bottom, is more responsible for surface water heating than people have given it credit for. We often talk about the warming temperatures in the Gulf of Maine, but concomitant with that is the salinity, and that's the key to what's happening. So we're seeing warm water come in at the bottom. And again, Henry Bigelow pointed out that the Gulf of Maine in the spring warms as much from beneath as it does from above. Now, in other words, the deep water warms the surface waters as much as surface solar and
All right, thank you, Dave. And so we're just 2 minutes past the time we're supposed to end. So thank you, everybody, for staying on. Thank you to Dave and Kay for your presentations. It was a final question, no, really a comment. Somebody said, really nice job by both presenters. So much analytical potential, especially as the sensors improve and come into more widespread use. Thank you. So again, thanks everybody. On the screen now, you can see my contact information, Dave's contact information, and Kay. So if you have any follow-up questions, please feel free to contact any of us. This webinar has been recorded, and we'll make it available on our website. And I believe a notice will be sent out to you, to everybody that registered. And please join us next Thursday at the same time to hear about the results from Great Bay and Narragansett Bay. And then on the following Friday, where we'll present more details about the sensors, some of the lessons learned, some of the challenges, and how to access the data from the project. So with that, thank you, everybody, and we'll bring this webinar to a conclusion.
and have left the webinar.